Hi there, Science 9. So today we're going to do a couple things. I just want to start out by talking a bit about your element project and then move on to a lesson I promised I'd give you about formulas and names for ionic compounds. So first of all, I'd like really just to remind you, please look at the handout you've got for the element project. I sent it, I believe it's an email attachment. It is definitely also in Teams. Specifically, what I'm looking for you to do is to pick a chemical element from the periodic table, one that interests you, and write up a project about it. The structure, I think, is given pretty clearly for my expectations actually in that handout. I'm looking for you to tell me what's the name of it, what's a Bohr diagram for it, what are some of its chemical and physical properties. A chemical property will be a way it interacts with other chemicals. A physical property would be something like its melting point and boiling point, and also some uses for that element. So all of this information is, much of it for a lot of elements is actually going to be in your textbook, but really you want to be drawing on the internet. Wikipedia has awesome pages for each of these elements, but don't feel obliged just to use that. That's part one of the project to be presented as a PowerPoint. Maybe you'd like to go with a Word file. I guess that would be fine. I've had a lot of students do this in the past and generally use PowerPoint with a lot of success. So the other part of that project is an experiment. I wanted to give you a lot of freedom on this one, giving you really two options. The first option is to do an experiment yourself. So you'll be working with that pure chemical element. Now, for this, of course, you're at home. You're going to have a limited range of possible elements that you can work with, but it's not like you don't have any. At home, you'll have probably easy access to, say, iron. You can produce pure carbon. You can be working with oxygen. You can do an ice cube tray battery, which is a pretty cool experiment. You can look that one up, ice cube battery. There would be lots of directions for doing that one. You have a lot of options. Paramount for that is you got to be safe. I say it in the description, like anything can be done safely, anything can be done not safely. So you know that when you go skiing, whatever, you're wearing a helmet. When you work with, say, with nails, you don't want to, cut yourself, or you don't want to get some of the solution in your eyes. These can all be worked with very safely. I haven't chosen anything that you can't work with safely. But that being said, maybe you want to see something that's a bit more spectacular and not do a reaction yourself. That's fine. I'd like to see some people doing experiments, but you don't have to. There are lots of videos, especially on YouTube, where you're on it right now, that show chemical reactions with a vast variety of elements. Channels like Periodic Table of Videos, Nerd Rage, Nile Red are three big channels for chemical experiments. They give lots of rich detail about what's happening and why they're doing it. So you can do that and just make sure you're ticking off those boxes. Make sure you've got, what's the objective of that experiment? What reaction are they trying to do? Why are they doing it? What materials did they use for it? How did they do it? What were their results? Just as if you were doing this experiment yourself, you're looking at someone else's video and figuring out what went on with their experiment. So that's all I wanted to say about that. Hopefully you're busy on that. I see actually some of you even finished that. That's great. Today we're looking at ionic compounds. There's piles of lessons you can find about this one on the internet. Like the Tyler DeWitt channel is great. But I also, of course, have my own spin on things. You can look in your notes package and you'll find directions for how to do this. But let's get started and see if we can get you really good direction for how to finish that handout that I've given you. First of all, some notes I've drawn up here. So reminder, ionic compound, what is it? Well, it's made from positively and negatively charged atoms. Those positively and negatively charged atoms are also called ions. So you might have, say, a sodium atom. That's sodium with the same number of protons as electrons, and as such we call it an atom of that element. But you can have a sodium ion. You saw us make some. When you strip its valence electron, you've got a sodium ion. Ionic compounds would be made out of ions, such as sodium ions. What happens with them is you make crystals out of them. A crystal is it's stacked. Think of it as a stack of positive and negative ions. If you look up images of ionic compounds on the internet, they'll show you the classic image is for table salt, sodium chloride. It'll show you sodium, chlorine, sodium chloride, sodium chloride, horizontally as well as vertically. Those ions are arranging themselves in a very specific way to maximize the distance between the positive ions, maximize distance between negative ions, but also minimize distance between the positive and negative ions. They are sucked together at the same time as ones with the same charge are pushed apart. This naturally forms a crystal structure. If you look at a crystal of table salt in your hand, you'll see it's a cube. But what people might not have always tried is if you can take one of these crystals of table salt and crush it like with a spoon or something like that. And if you look under a microscope at the crushed pieces of salt, they're still cubes. They're just much smaller cubes. It forms a cubic structure at any possible scale. There are salt mines deep in the earth where they get salt out from the ground to use it for whatever they need salt for. And you'll find that under the ground, they find giant salt crystals, but they're still cubes. Positive and negative ions are attracted. The negative and positive are repelled. They naturally stack to make that crystal arrangement. What we're looking at today is how do you name them? How do you give the formula for them? The name for a chemical compound, it's going to contain, at least for these kinds of chemical compounds, it'll tell you what elements are in it. Specifically, they're saying what elements as ions are in that chemical compound. For the chemical formula, they're saying the same information, except they're using element symbols. Here, I'll project what I wrote on the board. There. So the format for the names, here I'm just going to, you can pause the video there if you want to do that. Have a look what I wrote. Do that again, sorry. There. So the name of the format for the name is, it's like last name, first name. The first name of any ionic compound is going to give you the name of the positive ion. For these kind of chemical compounds, the simplest of all, arguably, the first name is going to be the metal, the positive ion. And the last name is going to be the non-metal, which is negatively charged. The formula, you're just saying the same thing, except you're communicating it using the element symbols. Now, for the metal, it's easy. The name of the metal ion is the same as the name of the metal itself. Table salt, sodium chloride. Sodium as a pure element with atoms is sodium. Sodium as ions, as part of that compound, you call it sodium still. So that doesn't change. But you want to communicate that it's an ionic compound. And you do that for these kinds of ionic compounds by dropping the last one or two syllables from the nonmetal and putting in instead the syllable, suffix IDE. Now, that gives you, for example, for the compound made of sodium and chlorine as an ionic compound, sodium chloride. Chlorine is the pure element. They drop the ene part from it and put on an ide. So now that is that cubic structure we call table salt, but we also call it sodium chloride. Now, the thing with chemical formulas that's a little bit trickier, because because then you're normally going to be taught how to do the naming first. The thing with the formulas is a bit trickier, is you've got to also state the number of ions involved, what's called the ratio. You've learned about ratios in math. You know a ratio is a little bit like a fraction. The number of this that I have for every one of this. You make a piece of pizza. You buy a pizza from the restaurant or something like that. And you cut it like that, like that, like that, like that. The ratio of pizza slices to pizzas is 8:1. There's 8 slices in each pizza. There's an example of a ratio for you from your real life. We need ratios to give the formula for ionic compounds. Yeah, let's get you a bit of light right there. Not that you really want to see me all that well anyways. I'm going to look through some examples of ionic compounds. Formulas specifically. Let's I'm going to draw them on the board, and then you can work with that. So let's say we make a compound. We take some aluminum, and we powder it, and we crush some iodine, and we put a drop of water on it. You get this explosive reaction. Purple gas is released. It's really cool to watch. Now, aluminum, if you look in the periodic table, you'll see its formula. Its element symbol is Al. You will also see that the charge on an aluminum ion is +3. You're stripping 3 electrons from it to make an aluminum ion, making it a +3 charge. Iodine, as an ion, is actually, it's going to have the symbol I minus. The minus means -1. That's light's not working. The minus means a -1. Forget about it. All halogens are the same way. Chloride, fluoride, they all have a -1 charge. Now, the rule for giving the formula for an ionic compound is the positive charges in the formula must balance the negative charges. It's a simple rule, but you always have to follow it. Now, the question is, how many iodide ions do I need to balance with the one aluminum ion? Aluminum is +3. Each iodide is a -1. So I guess we need 3 of them. The -3 from the iodide will balance with the +3 from the aluminum. So I'm going to draw 3 I minuses right here. Here. Oh, you can probably see that from here. See, I drew 3 I minuses. But how do you show that in the formula? You don't write it out like that. You write it out like this. Al, I, 3. 3 of the iodide ions for every 1 of the aluminum ions. Aluminum iodide is the name for this. Giving names is a lot easier than giving formulas. But once you get the rules down for giving formulas for binary ionic compounds, 2 elements, it's not so hard either. Let me just think of another one off the top of my head here. Okay. The obscure compound rubidium bromide. Rubidium is an alkali metal. You don't see it very often. I never have. But if you look on the periodic table, it'll tell you 2 things. It'll tell you that rubidium has got a symbol of Rb. Also, that it's got a +1 charge. It will tell you that bromine has a symbol Br. And it has a -1 charge. Well, this is actually very handy because the charges already balance. We're done. We just need to do this. We put them together, Rb, Br. And I guess it's a palindrome too, that's funny. But I want you to notice something. I want you to notice not only that I put them together, but when I put them together, I dropped out those charges. Common mistake. You don't need to have charges in the formula for the compound. It's kind of implied by what you already see there. If you take rubidium and bromine and put them together, it's going to make an ionic compound and a big bang. We know already, just from what's in the compound, that it's ionic. So you don't need to put down the charges. Let's look at another one. I'm going to do a couple with calcium. Calcium oxide, if you were to take some calcium and heat it under flame, I should try that, it would burn. It would be very bright and pretty spectacular. I'm going to try that later. Calcium, we can see from the periodic table, has got a +2 charge. Oxide, that is the oxygen ion, we dropped off the -ing part and we put an "ide" on there, has got a -2 charge. That's not bad either, because the charges are already balanced. We get +2 from the calcium ion, we get -2 from the oxide ion. The charges are balanced already, so we don't need subscripts. But now I'm going to do one that's a little bit more difficult. I'm going to do one where they've both got a subscript. They both have a charge, and the charge is not, it's not the same number. So let's go back here. Calcium. Calcium phosphide. First of all, phosphide ion is an ion of the element phosphorus. Where's that in the periodic table? It's a nonmetal, of course, because we're working with a binary ionic compound. The second elements are always nonmetals. It's got the symbol P, and the charge is -3. This looks like it's going to cause some problems. And I just told you that calcium has got a +2 charge. So how are we going to arrange these in a way that's going to work out for coming up with the correct chemical formula? You can't just say CaP2 or Ca2P, or it's just not going to work. You use the lowest common multiple. Lowest common multiple of 2 and 3 is 6. 2 times 3 is 6. It's divisible by 3 and divisible by 2. That 6 is going to be your total number of positive charges, and it's going to be your total number of negative charges. It's your magic number. If you want to know how many you need, you divide. You divide that lowest common multiple here by you divide by this charge here, 6 divided by 3. That tells us we need 2 of these phosphides. 6 divided by 2, the 2 from the calcium, tells us, well, the answer is 3. Ca2+. Ca2+. I think you can probably already tell, or will be able to tell with time, that this actually doesn't have to be all that difficult, and you can kind of do it in your head. But to start with, good to think this through or work this through with lowest common multiples, just like in the notes package. So what does this mean? Notice, I put 1, 2, 3 calcium ions here and 2 phosphide ions right here. This is going to tell us subscripts we need. Now let me be clear. The subscript is not the charge. It's not the charge. It's the number of ions in play that's going to give you your ratio of positives to negatives in terms of your number of ions that's going to be in that crystal structure. Well, there's 3 calcium ions and 2 phosphide ions. So there, I just told you the subscripts. Ca3, P2. And that's done as well. Now, I'm going to give you one more example there's a piece of information I'm going to leave out for now. Just hang tight for a second. I'm going to get a periodic table. Hey, perfect. This is awesome. Can make this simple. And now imagine we make an ionic compound from the elements zirconium and oxygen. I picked zirconium because it's got a +4 charge, and only a +4 charge. And I picked oxygen, well, you're going to see why I picked oxygen. So I'm going to put this over here. So we've taken some zirconium, and we combine it with oxygen. The name shouldn't be too hard to come up with. The name for the positive ion is just the name for the element already. The name for the negative ion, you're taking those last two syllables, the -ingen part of oxygen, dropping them and putting on an I. The compound made from the two of them is zirconium oxide. But we want a formula. Periodic table tells us the zirconium ion has a +4 charge, and an oxide ion has a -2 charge. So you might think, all right, 4 times 2 is 8. 8 divided by 4 is 2. 8 divided by 4 is 2. 8 divided by 2 is 4. And you come up with Zr2O4. Yes. Now, there's a little detail I need you to be aware of right here, and that is that you always want your subscripts to be expressed in the lowest possible terms. What would that mean right here? Well, for every 2 zirconiums, there's 4 oxide ions. But I think you probably know almost intuitively that you can express that differently. Imagine the fraction 2 divided by 4. Well, you can express that more simply. There's 2 2's in 4. 2 divided by 4 is 1/2, or 1/2. Here, our ratio is 2 to 4. But we can also express that as 1 to 2. So yes, you can use the lowest common multiple method, but in cases like this, you want to make sure it's expressed in the lowest possible terms. For the calcium phosphide, 2 and 3 had no common multiples, but 2 and 4 do. They're both multiples of 2. So Zr2O4, that's not the final answer. We've got to express that in the lowest possible terms. So I'm taking this away. Instead, I'm putting in here. I'm going to make a mistake right there. Look what I just did. And I'm going to fix it. I put in Zr1O2. This is a tiny mistake, but a lot of chem teachers are very picky. You never need to state a subscript of 1. If there's no subscript, it's assumed to be 1. This is why sodium chloride is NaCl. They don't say Na1Cl1. It's just NaCl. Really, that's all I want you to know for names of binary ionic compounds and formulas of binary ionic compounds. It's a pretty short worksheet. You're probably also busy with your other courses and your chemistry project for that matter. So yeah, let's just stick with that, although I will be giving you guys another lesson in not too much more time to take it to another level about naming and formulas for other kinds of ionic compounds. So thanks for tuning in.